So 10.2, we're going to keep working on. We've chunked it into some pieces. So today we're going to look at some different equations that allow us to make our lives a lot easier. So again, we're of course using the unit circle like we do all the time, but we're going to be using it a lot here because we're going to be converting between polar and rectangular, and then we're going to be using that to generate some rules. So we're going to say that this is polar form, which we've defined at this point. We're going to talk about two vectors, two complex numbers as vectors, I guess. So z1 is this complex number, and it has a magnitude of r, and it's got an angle of alpha. And then our second complex number has a magnitude of r sub 2, and we're going to call its angle beta. Okay, so we're going to show that z1 times z2 as a series of steps here, and our goal is to create a shortcut to make our lives way, way easier, right? That's always a good thing. So I wrote them out, and what we're going to do is we're going to FOIL or multiply component to component. So this one to this one to this one, and then we're going to just write our two magnitudes up front. So R1, R2, and then we're going to put cosine alpha, cosine beta, and then we're going to do these two components together. Okay, so those are the two blue ones. And then here we're going to do the two pink ones. Plus, let's say, I sine alpha cosine beta plus I squared sine alpha sine beta. Okay? And then these are all in parentheses because these two magnitudes are distributing to every component. So we're going to simplify here. There's our I squared. So anytime I see an I squared, I'm going to just cancel it out. Well, turn it into it's a negative 1. So this becomes minus down here. Minus. Okay. And then what you should see here is that we kind of have some special things that might look a little bit familiar to you. So here we have, maybe I'll grab another color out. Here we have cosine alpha, cosine beta, minus sine alpha, sine beta. So I'm going to write those up front. We still have R1, R2, and then cosine alpha, cosine beta, minus sine alpha sine beta. Okay. And then if you look at these components, both of the imaginary components together, it becomes plus I, I'm going to factor that I out, cosine alpha sine beta plus sine alpha cosine beta. Now maybe it doesn't pop out to you right away at this point, but it's something that you should start to look for more and more. So that this right here is one of our angle addition, and then this right here is our other angle addition. So cosine alpha, cosine beta is the same thing as cosine of alpha plus beta plus, and then this component right here, this is just our identity for adding sine angles together. I sine alpha plus beta. So this rule right here allows us to do really cool things with being able to add and subtract angles together when we were multiplying vectors. So we're going to look at an example tomorrow in class. So I want you to write down next to this C activity from class. And we're going to show with some pictures why this works. So this will be in our in-class activity. Be aware of that. Okay, so what we're going to do is we're going to show exactly what I told you here. We are going to show z1 times z2. So if I wanted to do it the long way, maybe it doesn't seem long right now, but if I wanted to do it the long way, I could FOIL them. So negative 2i plus 2 times 3 root 3 minus 3i, and I would multiply it out, and I would end up with a vector. So I would get negative 6 root 3i, and then I would get positive 6i squared, and then I would get positive 6 root 3, and then I would get negative 6i. Then I would combine like terms. Oh, there's an I squared, make it negative. Okay, so I would combine my like terms together. Here and here. So we would get 6 root 3 minus 6 minus 6i minus 6 root 3i. So that's not very friendly, but this is what it would look like in exact form as a vector. So we're going to do it using the rule here. So the first thing we have to do is write them in polar. So this is going to be, let's calculate our modulus here. It's going to be the square root of 4 plus 4, 8. It's going to be root 8. And then negative 2i, it's going to be down here, and positive 2 is our x, putting it right over here. Okay, and that's going to be 45 degrees below 360. So we're going to have cis 315. Okay. And then Z2 is going to be, let's determine our R for that. Square root of 3 squared gives us 9, times root 3 squared is 3, plus negative 3 squared is also 9. So this becomes 27 plus 9, which is 36, and that one worked out to be nice and friendly. So Z is going to be 6 cis, and then let's find the angle for this guy. Oh man. Where should I write it? I'll write it right here. So I need to figure out where this is. 3 root 3 and negative I is going to be down here. But in order for me to figure out what angle it's associated with, I'm going to go ahead and put it back into a unit vector form. So it becomes 3 root 3, scale it down, and negative 3i over 6, scale it down. So this becomes 2. So I have root 3 over 2, and then negative 1/2. So that puts it right about here, which is 30 degrees back from 360. So that makes that cis 330. Okay. So we FOILed it all out over here, and maybe this seems a little cumbersome because we're still practicing converting back and forth. But we're going to take z1 times z sub 2, and we're going to do it using this rule up here. So we're going to take root 8 times 6, and then we're going to take cis, and all we're going to do is we're going to add these two angles together. So 315 plus 330 is going to give us 645, which you may want to rewrite as a coterminal. So this becomes 2 root 2, 12 root 2, 645. That's one example of this. The next section we're going to do a couple other derivations. We're going to do dividing these out. We're going to come up with the derivation in the next video.